When sizing conduit for a UTP cable, firstly, follow the manufacturer's guidelines for the maximum number of cables per conduit size. Secondly, consider the bending radius of the cables. Thirdly, allow for sufficient space for pulling and servicing the cables. When considering wireway sizing for optical fiber, firstly, ensure that the wireway provides adequate protection for the fiber cables. Secondly, consider the bend radius and crush resistance of the fiber cables. Thirdly, avoid sharp bends or kinks in the fiber cables. UTP cables and fiber optics do not generate significant heat or electrical interference. However, if other cables, such as power cables, are present in the conduit or wireway, follow the same considerations for 480 volts alternating current or similar applications. Coaxial cables are not typically used in cable trays or conduits for UTP or fiber optics. Monoconductors are individual wires that can be used for various applications, including in cable trays. For a 12-inch cable tray, the number of conductors that can be accommodated depends on the fill factor and the conductor spacing. Assuming a fill factor of 40% and a conductor spacing of 1.25 inches, which is 31.75 millimeters, approximately 40 conductors with a diameter of 13.33 millimeters can fit in a 12-inch cable tray. Conduit sizing for electrical installations involves several crucial steps to ensure safety and compliance with the National Electrical Code, or NEC. Firstly, you must determine the total cross-sectional area of all conductors that will be installed within the conduit. This is typically found in NEC Chapter 9, Table 5 and Table 5 for individual conductor dimensions. For cables, refer to the manufacturer's specifications. Secondly, select the appropriate conduit type based on the environment and application. Common conduit types include electrical metallic tubing, or AIM, rigid metal conduit, or RMC, and rigid polyvinyl chloride conduit, or PVC. Each type has different properties regarding corrosion resistance, strength, and installation requirements. Thirdly, use NEC Chapter 9, Table 4 to determine the maximum allowable fill percentage for the selected conduit type. Different conduit types have different fill limitations. For example, for 3 or more conductors, the maximum fill is typically 40%. Fourthly, calculate the allowable conduit fill area. Multiply the conduit's internal area by the allowable fill percentage. The internal area of the conduit can be found in NEC Chapter 9, Table 4. Fifthly, compare the total cross-sectional area of the conductors with the allowable conduit fill area. The total conductor area must not exceed the allowable fill area. If it does, you must increase the conduit size. Sixthly, consider directing factors for conductors and conduit. When multiple current-carrying conductors are bundled together in a conduit, their ampacity must be derated according to NEC Table 310.15. This derating is necessary to prevent overheating. Seventhly, check NEC Chapter 9, Annex C for examples and detailed calculations related to conduit fill. Eighthly, always refer to the latest edition of the NEC and local codes for specific requirements and updates. Ninthly, ensure that all conduit installations comply with NEC Article 300, which covers wiring methods and materials. Tenthly, when pulling conductors through the conduit, use appropriate pulling lubricants to reduce friction and prevent damage to the conductor insulation. Always consult with a qualified electrician or engineer for complex installations or if you have any doubts about the calculations. Wireway sizing is another critical aspect of electrical installations, ensuring that conductors are properly housed and protected while adhering to the National Electrical Code, or NEC standards. Firstly, determine the number and size of all conductors that will be placed within the wireway. This includes considering future expansion needs. Secondly, select the appropriate type of wireway based on the environment and application. Common types include metal wireways, non-metallic wireways, and auxiliary gutters. Each type offers different levels of protection against physical damage, moisture, and corrosion. Thirdly, calculate the total cross-sectional area of all conductors. Refer to NEC Chapter 9, Table 5 and Table 5 for conductor dimensions or consult the cable manufacturer's specifications. Fourthly, use NEC section 376.22 for metal wireways or NEC section 376.23 for non-metallic wireways to determine the allowable fill percentage. The NEC specifies that the sum of the cross-sectional areas of all conductors shall not exceed 20% of the interior cross-sectional area of the wireway. Fifthly, calculate the minimum required size of the wireway. Divide the total conductor area by the allowable fill percentage to determine the minimum interior cross-sectional area of the wireway. Sixthly, select a wireway size that meets or exceeds the calculated minimum size. Wireway dimensions are typically provided by the manufacturer. Seventhly, consider directing factors for conductors and wireways. According to NEC section 376.22, conductors and wireways may require ampacity directing if the number of current carrying conductors exceeds 30. Eighthly, ensure that the wireway is properly supported according to NEC section 376.30. Supports must be provided at intervals not exceeding 5 feet for metal wireways and 3 feet for non-metallic wireways, unless otherwise specified by the manufacturer. Ninthly, check NEC Article 376 for specific requirements related to wireway installations, including bonding, grounding, and conductor identification. Tenthly, provide adequate spacing between conductors to facilitate heat dissipation and prevent overheating. This is especially important in wireways with high conductor densities. 11thly, always refer to the latest edition of the NEC and local codes for specific requirements and updates. 12thly, when installing conductors and wireways, ensure that they are properly identified and labeled. 13thly, consult with a qualified electrician or engineer for complex installations or if you have any doubts about the calculations. Understanding the different types of cables, such as unshielded twisted pair or cable and fiber optic cable, is essential for designing and maintaining efficient and reliable communication systems. Firstly, unshielded twisted pair or cable consists of pairs of wires twisted together to reduce electromagnetic interference or EMI and crosstalk. UTP cables are commonly used in Ethernet networks for data transmission. Secondly, fiber optic cable transmits data as light signals through thin glass or plastic fibers. Fiber optic cables offer higher bandwidth, longer transmission distances, and immunity to electromagnetic interference compared to UTP cables. Thirdly, UTP cables are categorized by performance standards such as Category 5E, Category 6, and Category 6. High categories offer improved data transmission rates and reduced crosstalk. Fourthly, fiber optic cables are available in two main types: multimode and single mode. Multimode fiber is used for shorter distances, while single-mode fiber is used for longer distances and higher bandwidth applications. Fifthly, UTP cables are typically terminated with RJ45 connectors, while fiber optic cables are terminated with various types of connectors such as LC, SC, and SD connectors. Sixthly, when installing UTP cables, it is important to maintain the proper bend radius to avoid damaging the cable and affecting performance. The recommended bend radius is typically 4 times the cable diameter. Seventhly, fiber optic cables are more sensitive to bending and physical stress than UTP cables. They should be handled with care to avoid damage to the fibers. Eighthly, UTP cables are susceptible to electromagnetic interference or EMI from nearby electrical equipment. Shielded twisted pair or STP cables can be used to reduce EMI in noisy environments. Ninthly, fiber optic cables are immune to electromagnetic interference, making them suitable for use in environments with high levels of electrical noise. Tenthly, UTP cables are relatively inexpensive and easy to install, making them a popular choice for many network applications. 11thly, fiber optic cables are more expensive than UTP cables and require specialized equipment for installation and termination. 12thly, UTP cables are limited in distance due to signal attenuation. The maximum recommended length for UTP cables is 100 meters. 13thly, fiber optic cables can transmit data over much longer distances than UTP cables, ranging from hundreds of meters to several kilometers, depending on the fiber type and transmission equipment. Fourteenthly, UTP cables are commonly used in office buildings, homes, and other indoor environments, while fiber optic cables are used in data centers, telecommunications networks, and other high bandwidth applications. 15thly, when selecting between UTP and fiber optic cables, consider the bandwidth requirements, transmission distance, environmental conditions, and budget constraints of the application. 16thly, always follow the manufacturer's recommendations and industry best practices when installing and maintaining UTP and fiber optic cables. The National Electrical Code, or NEC, provides guidelines for installing electrical cables and raceways in various environments to ensure safety and prevent electrical hazards. Firstly, NEC Article 300 covers general requirements for wiring methods and materials, including cable installation. Secondly, NEC Article 310 provides requirements for conductors for general wiring, including ampacity, insulation, and installation. Thirdly, NEC Article 314 covers outlet boxes, device boxes, and pull boxes, which are used to protect wiring connections and provide access for maintenance. Fourthly, NEC Article 330 covers metal-clad cable, or MC cable, which is commonly used for branch circuits and feeders in both exposed and concealed locations. Fifthly, NEC Article 334 covers non-metallic sheath cable, or NM cable, which is commonly used for residential wiring. Sixthly, NEC Article 344 covers rigid metal conduit, or RMC, which is used for protection against physical damage and corrosion. Seventhly, NEC Article 348 covers electrical metallic tubing, or EMT, which is a lightweight conduit used for protection of conductors in dry locations. Eighthly, NEC Article 352 covers rigid polyvinyl chloride conduit, or PVC conduit, which is used for underground and corrosive environments. Ninthly, NEC Article 358 covers electrical non-metallic tubing, or ENT, which is a flexible conduit used for concealed wiring in dry locations. Tenthly, NEC Article 366 covers auxiliary gutters, which are used to supplement wiring spaces at meter centers, distribution centers, and similar locations. 11thly, NEC Article 370 covers cable trays, which are used for supporting and routing cables in industrial and commercial applications. 12thly, NEC Article 392 provides requirements for cable trays, including allowable fill, support, and grounding. 13thly, when installing cables and raceways, it is important to follow the NEC guidelines for spacing, support, and protection from physical damage. 14thly, all electrical work should be performed by qualified electricians who are familiar with the NEC and local codes. 15thly, regular inspections and maintenance are essential to ensure that electrical systems are safe and compliant with the NEC. 16thly, always refer to the latest edition of the NEC and local codes for specific requirements and updates. When considering hot and interference issues in electrical installations, it's essential to address several factors to ensure safety and reliability. Firstly, heat generation in conductors is a significant concern. When electrical current flows through a conductor, it generates heat due to the conductor's resistance. This heat can cause insulation breakdown, reduce conductor lifespan, and even fire hazards. Secondly, the ampacity of conductors is the maximum current a conductor can carry continuously without exceeding its temperature rating. The National Electrical Code, or NEC, provides ampacity tables in Article 310.15, which must be followed to prevent overheating. Thirdly, dating factors must be applied when multiple current-carrying conductors are bundled together in a conduit or cable tray. The NEC requires ampacity to be dated to account for the increased heat generated by multiple conductors in close proximity. Fourthly, ventilation and cooling methods should be considered in areas with high conductor densities or high ambient temperatures. Proper ventilation can help dissipate heat and maintain conductors within their temperature ratings. Fifthly, electromagnetic interference, or EMI, can disrupt the operation of sensitive electronic equipment. EMI can be caused by various sources, including power lines, motors, and electronic devices. Sixthly, shielding techniques can be used to reduce EMI. shielded cables, conduits, and enclosures can block or reduce the transmission of electromagnetic radiation. Seventhly, grounding is critical for minimizing EMI and ensuring safety. Proper grounding provides a low impedance path for fault currents and helps to reduce voltage transients. Eighthly, surge protection devices, or SPDs, can protect equipment from voltage surges caused by lightning strikes or other electrical disturbances. SPD should be installed at the service entrance and at sensitive equipment locations. Ninthly, filtering can be used to reduce EMI on power lines and signal cables. Filters can block or attenuate unwanted frequencies, improving the performance of electronic equipment. Tenthly, separation of power and signal cables is important to minimize EMI. Power cable should be routed away from signal cables to reduce the risk of interference. 11thly, regular inspections and testing should be performed to ensure that electrical systems are operating within safe temperature limits and that EMI is being effectively controlled. 12thly, always refer to the latest edition of the National Electrical Code, or NEC, and local codes for specific requirements and updates related to heat and interference mitigation. Understanding fill factors and conductor spacing is crucial for ensuring the safe and efficient operation of electrical systems, particularly in cable trays and conduits. Firstly, the fill factor refers to the percentage of the cross-sectional area of a conduit or cable tray that is occupied by conductors. The National Electrical Code, or NEC, sets limits on the maximum allowable fill factor to prevent overheating and to ensure that conductors can be easily installed and maintained. Secondly, NEC Article 300.17 specifies that the number of conductors in a raceway shall not exceed that which will permit the dissipation of heat and ready installation or withdrawal of conductors without damage to the conductors or their insulation. Thirdly, NEC Chapter 9, Table 1 provides the maximum allowable fill percentages for different types of raceways. For example, for 3 or more conductors in a conduit, the maximum fill percentage is typically 40%. Fourthly, to calculate the fill factor, you need to determine the total cross-sectional area of all conductors in the raceway and divide it by the internal area of the raceway. The internal area of the raceway can be found in NEC Chapter 9, Table 4. Fifthly, conductor spacing refers to the distance between conductors in a cable tray or wireway. Proper conductor spacing is important for heat dissipation and to prevent the spread of fire. Sixthly, NEC Article 392.22 specifies the allowable fill for cable trays. The sum of the cross-sectional areas of all cables in a cable tray shall not exceed the maximum allowable cable fill area specified in Table 392.22. Seventhly, when installing single conductor cables in a cable tray, NEC Section 392.20 requires that they be installed in a single layer with a minimum spacing of 1 cable diameter between adjacent cables. This spacing helps to dissipate heat and prevent overheating. Eighthly, when installing multi-conductor cables in a cable tray, NEC Section 392.20 allows for the cables to be stacked, provided that the cable tray is designed to support the weight of the cables and that the cables are not damaged during installation. Ninthly, the NEC also specifies requirements for bonding and grounding cable trays to ensure electrical safety and to minimize the risk of electrical shock. Tenthly, always refer to the latest edition of the NEC and local codes for specific requirements and updates related to fill factors and conductor spacing. 11thly, consult with a qualified electrician or engineer for complex installations or if you have any doubts about the calculations. 12thly, proper planning and careful installation practices are essential for ensuring that electrical systems are safe, reliable, and compliant with the NEC.